A lot of the time, building distributed systems can feel a little bit like this. A request comes into your system, you get a tangled mess of interconnected service calls, and then hopefully, maybe some output you expect comes out the other end. And I can see some of you nodding like you can relate to this picture. And that's because distributed systems are hard. And almost every modern software system deployed to the cloud is a distributed system in some way. There's no real escaping it. Now, some of you are probably here because you've had problems with distributed systems in the past. Those of you nodding along to this diagram who can relate. But there's also probably some of you here who are new to the world of software, who are new to development, who want to avoid some of the pitfalls that come with building distributed systems. And that's what you're going to learn about in this talk today. You're going to learn how you can leverage best practices, patterns that you can implement when building distributed systems to help build more resilient, available, and most importantly, evolutionary systems on AWS. I'm James Eastham. I'm a senior cloud architect here at AWS. And for the rest of this talk, you're all going to need to put on your imagination hats, because you're all going to be developers for a completely fictional e-commerce company. And this is the system architecture you have today. And you're all incredibly good developers and architects. So you've thought about microservices. You've thought about bounded contexts, about decomposition. You've designed your system in a way that ensures you have high cohesion in your system. You're working with microservices. But as you've added more and more services, you've added more and more lines of synchronous communication. And what you've actually ended up with here is a distributed monolith. And now you need to add a new AI-powered search service to your system. And to do that, you now need to go and make changes to two other microservices that you have no control over. You need to get into their feature backlog. You need to get into their release cycles. Your ability to scale, to adapt to change, has been slowed down by the architecture decisions that you chose to make. But you're all smart developers, remember. And you think, there must be a better way of doing this. Surely there must be a better way. And that's what you're going to work towards throughout the rest of this talk. You're going to work towards something that is loosely coupled, to give you services that can truly be developed and deployed independently and evolved over time as your requirements change. That is the promise of building event-driven systems. But to start with, let's start small. Let's start with these two services here. Because, of course, systems still need to communicate. There is a difference between a loosely coupled system and a decoupled system. A decoupled system would point towards there being actually no integration at all, and it's really quite hard to get anything meaningful done if your services can't communicate. So the first step on this journey to building better distributed systems is to think about inter-service communication. How do your services communicate? Because when you're building distributed systems, how things communicate is incredibly important. What used to be a simple method call inside a single process running on a monolith is now running across a network. And how many of you love working with networks? Oh, I see some hands. Awesome. And when you first think about this, synchronous communication, it looks kind of simple, doesn't it? You have one service that makes a HTTP request to another service. And this is fantastic when things are on the happy path. How many of you have ever built a system that has never once strayed from the happy path? OK, I see some hands. Can you come and catch me afterwards, please? I'm interested to know what you're building. And because things go wrong, don't they? Things break. And they can break in wonderful and magical ways. When you're building these synchronous communications, the first question becomes, where is the other service that I need to communicate with? And you might say, well, easy. DNS exists for that. I can make a call to loyalty.ecommerce.com. But what happens if the loyalty service isn't actually there? How do you code for that? And even more subtly, what if it is there, but it responds incredibly slowly? A really fast 404 response is much easier to deal with than a 200 response that might sometimes maybe take 15 seconds. And when you think about this point of integration, is it even correct? Should the order processing service really care about the fact that people are collecting loyalty points? Possibly, but possibly not. And these are the kind of questions that you need to get into as you develop distributed systems that focus on this more synchronous style of communication. But remember, you're still all smart developers and architects. So you're all thinking, well, let's change this up a little bit. Let's start to think more asynchronously. Let's start to think more event-driven. As you communicate between different bounded contexts, between different areas of your system, prioritize asynchronous communication wherever possible. Because now, as a developer of the order processing service, you don't need to care where the loyalty point service is. You don't need to care about the DNS. You don't need to care about the network routing. Now, if you're one of them people who put your hands up, obviously you can still care if you want, but you don't need to if you don't want to. And when you think about this logically, this actually makes a lot more sense. The order processing service publishes an order completed event, and the loyalty point service is really interested in that event and goes off and increases the loyalty points. Now, when it comes to building on AWS, there are, of course, two serverless services that can help you here. They're Amazon EventBridge and Amazon SNS. Both support publish subscribe, which might lead you to ask the question, which is the right service to use? And they are very similar. They do both provide publish subscribe capabilities. Architecturally, things do differ slightly. SNS is topic-based communication. So typically, each type of event you're going to publish will be published onto a separate SNS topic. What that means as a subscriber is that you need to know the location of all these different topics for all these different types of event. Whereas with EventBridge, typically you would have a single or maybe a small number of buses that the producer is producing events to. And then your subscriber can define rules on the EventBridge to define which events they are interested in. So there are some architectural differences. There's also some other differences that will be driven by the business requirements that you have in your system. So let's imagine you need to guarantee the order of events. Well, SNS supports first-in, first-out topics, or FIFO topics. EventBridge doesn't guarantee any kind of ordering. Or maybe you need to send your events directly to a person. SNS supports app-to-person notification using text or email or push notifications. And finally, depending on what the service is that you need to integrate with what you're targeting, EventBridge supports roughly 3 times as many targets as SNS does. So both services are incredibly useful. They both provide different types of publish-subscribe capabilities. And you can use them together. In your order processing domain, inside that bounded context, ordering is incredibly important to you. So you use SNS, you use SNS FIFO, and you've got a service interested in them events that are going to be processed in order. But when you then come to integrate with a service outside of your control, ordering becomes less important. So you might use another service to publish to EventBridge, and then your loyalty point service can subscribe to EventBridge. The important takeaway here is to let your business requirements drive your choice of service. Now, when you're thinking about building things in an event-driven way, this component here becomes incredibly important. If you think about when you're building synchronous microservices, you typically never expose the structure of an internal domain object outside of your API. And the same applies when you're building events. Once you start integrating with services outside of your control, you typically want to have some kind of translation layer, something that takes that internal event and translates that into a public event, and that then allows you to develop the two independently. And this also applies if you're a developer of the loyalty point service, if you're building a subscriber, because you're now receiving events from an upstream service in a completely asynchronous way. Frankly, you might never even talk to that team, so you have no way to control what they're going to do. And actually, because we all love these laws in software, there's a really good law that helps define this. That's Postel's law. Be conservative in what you do, and be liberal in what you accept from others. So when you're building your subscribers, be really careful with what you do. Instead of subscribing your compute, whatever that might be, whether that's a container, whether that's a Lambda function, instead of subscribing that directly to your bus, introduce some kind of layer in between. In this case, an SQS queue. So if there's suddenly a massive influx of events that you don't expect, or an event that has a different structure that causes your system to break, you've protected yourself against that. You can do that using dead letter queues. You can route these events off to dead letter queues. And I know what you're all thinking now. This is going to be the shortest 40-minute talk ever because we can all celebrate because we're building event-driven systems. Job done, dust our hands, let's go and get a beer. If only such a silver bullet existed, it would all be wonderful, wouldn't it? How many of you have ever had to deal with change in a system? Whether that be you need to implement a new feature, a new functionality, new team members. Again, those of you with your hands down, please come and grab me afterwards. I want to know what's not changing. And that's because change is really hard. The most resilient system you will ever build is one that never needs to change. And you might think, well, James, I've taken this big tangled mess of service calls and I've streamlined that. I've made it all lovely. Everything's event-driven. It's asynchronous. It's fantastic. If only it was that simple. Let's come back to this same integration point again. So the order completed event gets published by the order service. And you're a developer of the loyalty point service, and you need to implement the functionality to add 10 loyalty points every time someone spends £1. So you set up the rule, you go and have a look at the order completed event, the payload that actually comes in, and it looks like something like this. Not very useful if you need to know the value of the order, right? The value of the order isn't there. And this is an example of what's called a notification event. A notification event is a really lightweight, really simple event that simply notifies another system that there's been a change in state. But it provides very little context about exactly what has changed in the entity. And if you're using these thinner notification events, it typically leads you to needing a pattern that looks something like this. So you have your subscriber that defines the rule. They receive that order completed event. And then you need to make a synchronous API call back to the order processing service to get the value. And now you've just kind of moved that synchronous API call around, haven't you? But this is where you start off. And this is functionally perfectly good. It's a perfectly great way of doing this kind of integration. But you think again, is there a better way of doing this? So you go and have a conversation with the order processing team. You collaborate briefly. And you end up changing the event that gets published to look something like this. So now the order value is being passed as part of the event. And you're incredibly happy now as a developer of the loyalty point service because you don't need that synchronous API call. You can now integrate with that service in a loosely coupled way. Yay for us. And if you fast forward 6 months, this gets even better because you've now managed to add an analytics service without touching any other service. You're evolutionary. You've adapted your system to change. And now you're all definitely thinking, it must be time to celebrate, James. It must be time for that beer. If only. Because your e-commerce website is growing. You've now gone global. You need to support multi-currencies. And your analytics service is interested in the currency of the order. So now your analytics service needs to implement this synchronous callback to go back and get the currency of the order. And much like the loyalty point service did, the analytics service will go and have some collaboration with the order processing service, and they agree a change to the event that changes the event from this to this. Anybody see an issue with us doing that? Especially if you're a developer of the loyalty point service? Yeah, because although the analytics service is now incredibly happy because they can remove this line of synchronous communication, the loyalty point service is incredibly sad because they've just been broken by a system they didn't even have any control over. Now, because you're all smart developers and you're all listening to this talk, you've got dead letter queues, you've got error handling. So although this doesn't directly break your system, it means that people aren't getting their loyalty points. And this is an example of what you could call YOLO eventing. Because these event payloads are just JSON, you can just change them however you need to, right? Now, there is a better way to manage this. And I'm going to put a word on the screen in a second, and it's a really naughty word, and I'm sorry, none of you are going to like it. You're going to get like these shivers down your spine, and I'm sorry. And that word is governance. Yeah, hard to say sometimes. Because it fills you with this feeling of bureaucracy, doesn't it? And red tape, governance, you have to govern things. But it doesn't need to be bureaucratic. You can govern things in a way that is asynchronous as well. And you can do that using a process you're probably all familiar with. That's the idea of an RFC, or a request for comment. So whenever it comes to you making changes to these events, you would first raise an RFC, proposing the change to the event that you're going to do. And as a developer of the loyalty point service, you'll see that RFC, and you'll put a comment on it, and you'll say, please don't change that in that way. And the order processing service can take that on board and instead change the event payload to look something like this. So now everyone's happy. The analytics service has their currency, the order processing service still has their value, people still get their loyalty points. Schema management is incredibly important as you start to build systems this way. Your ability to evolve and change your system over time when you adopt asynchronous communication is going to be determined by how well you can develop schemas, or change your schemas. And we've introduced two types of events here, notification events, and these fatter event-carried state transfer style events, where the state of the entity is carried as part of the event. And you might then naturally think, well, which is the right one to use? And at risk of sounding really cliche, of course, it always depends. And I promise you that's the only time I'll say it depends in this talk. Because both types of event still have their own unique types of coupling. A notification event will probably give you more coupling at a service-to-service level, because you might need that synchronous callback. But imagine you have 100 consumers of an event, and only one of them needs to call back. Well, then that might not necessarily be a problem. If you adopt this style of events where you have more data in there, your coupling moves from more service-to-service runtime coupling into something more semantic. Your coupling is at your schema level, and you need to have governance and good change management practices in place to ensure that you don't break systems that you don't even know exist. And as far as a heuristic goes here, I'd like to come back to Postel's law. And particularly the first part of Postel's law, be conservative in what you do. Be incredibly intentional about what you include in your events. And then if you find a specific consumer is making a lot more callbacks than another consumer, well, then you can collaborate with them and find out how you can improve the event to make it better over time. And whichever type of event you choose, be really careful how you manage the schemas. Bring in some kind of defined way of defining events. Use something like the cloud events specification. This is a defined specification that a bunch of really smart people came up with, and it was actually in the adopt ring of the most recent ThoughtWorks Tech Radar. And it provides a consistent schema that every single event across your entire organization will follow. And there's some really important fields in here. You've got this data field. This is the actual payload. This is the actual event. What's in here is going to be different for every single type of event in your organization. You've got this ID field. This is a uniquely generated identifier generated at the point of publish. And this allows you to determine things like cause and effect, and to implement things like idempotency, so the consumers can understand if they've seen a specific event before. And really importantly on this conversation about dealing with change, the type field. Now, of course, this includes the type of event, order completed. When you're defining rules on EventBridge, this is typically the field you're going to use. What you'll notice is there's also a version number in that event type. And this is what will allow you to implement things like breaking changes, to handle these changes that you're going to need to make at some point. So as a developer of the order processing service, you need to make a breaking change. So what you're going to do is you're going to make that breaking change, but you're going to publish two versions of the same event, version 1 and version 2. You're going to publish them at the same time. Your downstream services are going to define rules that are specific to a specific version. So right now, today, both of the subscribers are subscribing to version 1. And it's the analytics service that's really interested in that currency field, so they're immediately going to update themselves and start processing version 2. The loyalty point service are kind of, meh, we'll do it at some point. So eventually, the order processing service will stop publishing the event. They're only publishing version 2. The loyalty point service also updates itself to use version 2. This keeps you asynchronous, it keeps you evolvable, while still allowing individual teams to make changes that they need to make based on their specific business requirements. So now you've got this lovely, wonderful, loosely coupled system. It's prioritizing asynchronous event-driven communication. You've removed many of the lines of synchronous communication. And then you hit another challenge. When an order first gets created, you need to ensure that there's a set of things that happen before you do anything else. You need to ensure that a payment has been taken, that the order's in stock, that there's someone to deliver the order. There's all these things that you need to do. And if any one of them things fail, of course, you don't want to let the order go through. Now, if you were building a non-distributed system, you'd probably handle this with something like a database transaction. You'd open a database transaction, you'd do all the writes that you need to do, and if at any point something fails, you just roll back the database transaction. When you're building distributed systems that don't share databases, this can get tricky. Because you'll almost definitely have processes in your businesses that are end-to-end workflows that span multiple different microservices. And if you're building things in a purely asynchronous way, all you've got really now is messages and events just kind of flying around your system everywhere. And sometimes you'll have situations where things need to be processed in order, where you need to manage the overall state of a given entity. Or maybe you just want to know what the heck is going on. You need some visibility into the workflow. Now, there's a number of different approaches you could take to solving this kind of problem. One of those is orchestration. For example, in music, an orchestra consists of lots of individual musicians, each with their own program, their own sheet music. They're all doing their own individual thing, but they come together as a whole to actually make some lovely sounding music. So let's contextualize this in your e-commerce website. For the next part of this talk, you're going to zoom in on this order processing service again. This is the core component of your system. If people can't place orders, well, you've not really got a very useful e-commerce website, do you? And inside this order processing service, there's a lot of different things that need to happen. As we said, you need to check the stock of an order. You need to reserve the stock. You need to take the payment. You need to ensure there's someone to deliver the order. And there's all these things that need to happen across multiple different services. And you might be thinking, James, you've just told us that everything should be asynchronous and event-driven and wonderful. So how does this help me? Orchestration is really useful when you want to do any of the things on screen here. You need to do things in sequence. You need to retry failures. You want to do multiple things in parallel. And remember, these kinds of operations probably already exist in the systems you are building today. But by referring to them as the pattern they actually are, it helps you surface up and talk about some of this complexity. So thinking about patterns of distributed systems again, we're going to talk about another pattern now, and that is the Saga pattern. Is anyone familiar with the Saga pattern, by the way? A few hands. OK, cool. So a Saga consists of a series of local transactions. So think of a local transaction as an individual microservice doing its own individual piece of work, including writing to a database, doing some stuff. Now, a Saga understands which sequence of these local transactions need to happen in what specific order. The Saga also understands, really importantly, how to roll back or how to compensate for failures. So if at any point one of these local transactions fails for whatever reason, the Saga will understand how to undo the actions that have already been done. And a Saga is typically made up of 3 key parts. And I'm going to really stretch this classical music analogy now, just bear with me. The first part of a Saga is some kind of orchestration engine. Think about this as the conductor in the orchestra, someone who's managing this kind of end-to-end workflow. You've then got the individual steps, the individual microservices. Think of this like the individual sections of the orchestra. You've got the string section, the percussion section. They're all doing their own individual thing, orchestrated by the conductor. And then where this classical music analogy really falls down is where you think about these transactions and these compensations, where something doesn't work quite right, then the Saga can compensate for that and roll back. The best I can think of here is that if the violin section's playing faster than they should do, then the conductor tells them to speed up. As you can probably tell, I know nothing at all about being a conductor, but that's how I kind of imagine it works. Now, before we get further into the Saga, you can still manage these kind of problems using a purely event-driven approach. And if you caught Julian and Michelle's talk earlier, they talked a little bit about this difference between orchestration and choreography. So using a purely event-driven approach is more like choreography, where you've just got these events flying around. Each individual system knows which event it's interested in, does its own piece of work, and publishes another event. And the end-to-end business workflow will still happen. It's just that it's kind of all happening as individual components. And this typically makes it cheaper because you've not got this centralized orchestrator. And it typically makes it easier to scale independent components. Where this gets difficult, though, is when you need to determine things like cause and effect. Things like observability do become tricky. Orchestration is typically more similar to a non-distributed system. You've got one central system that's making calls out to lots of other systems. It's simpler to build and to operate and to understand. So let's go through this actual Saga that you're going to build now. So the Saga understands how to hold stock, how to create a delivery record, and then how to issue the loyalty points. The Saga also understands how to release the stock, how to cancel the delivery, and how to take back people's loyalty points if anything fails. And of course, you've already made one component of this event-driven. You've already built that integration between the order service and the loyalty point service, and that is now using events. And these things can work together. It's not that you have to do orchestration or you have to do choreography. Here, you might orchestrate the first part of the order processing flow using a Saga, and then at the end of that, publish your order completed event that the loyalty point service can then react to. So let's think about actually building this Saga now. So the steps of the Saga are going to be that you create the order record in the database. The order comes in, you create it. You need to go off and reserve the stock. You need to talk to the inventory service. You need to actually organize the delivery of the order using some kind of fulfillment service. And then finally, the order is completed. You publish the order completed event. The Saga also understands for each individual step of this workflow how to undo that step. So if the order creation fails for whatever reason, well, you want to archive the order. You don't want this kind of half-created order just hanging around. It also understands how to release the stock, how to give the stock back. It understands how to cancel the delivery. It understands how to do all of these compensating actions. And of course, this is all great on the happy path. And you could go and hand code all of this in whatever programming language you choose. You could write if statements, you could write try catches, you could do all that stuff yourself. Or you could use a service like step functions. Step functions at its core is a workflow engine. It allows you to build these complex workflows to orchestrate different AWS services and microservices. Them different behaviors I talked about earlier, things like sequencing, error handling, retries, callbacks. Step functions has that all natively built in. And it also comes with direct integrations with over 250 AWS services. That means you can call over 11,000 APIs directly from within your workflow. Now, in the context of this example, step functions is going to be your order processing orchestrator. So let's actually look at this first part of the Saga. You need to create the record and then actually handle the calls to the inventory service. And this is what that might look like in step functions. So the first thing you're going to do is create the order record. You're operating inside the order processing domain now. So that's just a call to a Lambda function, some code that you manage to actually do some business logic to create the order. And then you're going to reach out to the inventory service and actually get the current stock level and reserve the stock. And if that succeeds, then happy days, you go on and the workflow completes. If that fails, then you're going to release the stock and then archive the order. You've got them compensating transactions. And you'll notice some of the lines there, they've got words like catch on them. Things like error handling are built into this. So if that first Lambda function fails for whatever reason, step functions is going to handle the routing to route that to the archive order step. You don't need to think about that. If you scale this up now to the entire workflow, you'll notice that this kind of just repeats itself a little bit. You've got a call to the inventory service if that succeeds. You've then got a call to the order routing service, the fulfillment service. And you'll notice right down at the very bottom, there's two publishes of events to EventBridge. That's to publish your order completed or order failed events. Now, the observant amongst you have probably noticed that this is using API Gateway, and we've just spent half an hour talking about how synchronous calls you're trying to want to avoid. And that could equally be publishes of events. Step Functions has a really cool feature called Wait for Callback, where you can make an AWS API call and pass a task token along with that payload. And the Step Functions workflow is going to pause. It's going to wait until it gets a call back to say, please continue. So you could equally replace them synchronous API calls with something more event-driven. So this talk so far has been primarily focused on patterns. And fundamentally, what we've done here is just selected the right pattern to fit the right problem with building distributed systems. And if you're really interested in patterns, there was a book written 20 years ago that is just as relevant now as it was then. It's one of my favorite programming books ever. Actually released in 2004, which was the same year as Domain-Driven Design, which was a fantastic year for software books, if you ask me. So to come back to that question, do we use orchestration or do you use choreography? And here you want to let your business requirements drive your choice again. And you'll probably almost always find this is an and conversation. In your e-commerce example, this process of taking the payment of an order, checking the stock level, you want to absolutely guarantee that happens before you take your order any further. So in that case, you probably want to use orchestration. You want to orchestrate that business flow to ensure that it completes as you expect. But when it comes to that integration with the loyalty point service, something that isn't really on the core path, something that's cross-domain, then you might lean towards choreography, where you're taking a more event-driven, asynchronous approach. So now you're in this wonderful asynchronous world, but there's one other topic that I just wanted to touch on really quickly, and that's the idea of security in event-driven systems, particularly with sensitive data. So let's take a look at a sample event payload. Thinking about sensitive data, does anybody see any issues with this event payload? Of course. Please, nobody include a plain text card number in your events. Please don't do that. But of course, there are scenarios where you might actually need to share this PII or PCI data. So how can you actually do that? Well, one option would be to follow the Postau's law and be really conservative. Just don't include this information at all. But if you do need to include it, make sure you encrypt it. And you can actually be really tactical how you do this. If you're using a service like KMS, you can encrypt that payload with a KMS key and publish that onto an event bus that every single other service is allowed to consume. That means every single other service can do work based on that event. But then the actual key, you only allow certain services permissions to access the key in KMS. And that means, in this instance, only the marketing service has the ability to actually decrypt that sensitive data. OK, you've spent a lot of time imagining in this talk so far. What if you sat there thinking, now, well, I've not really got an e-commerce website, James. I've got another use case. So let's actually talk really quickly about how you can start to get started with this kind of process. And the first thing I always say is to start by creating an event bus per domain. Don't try and bring event-driven architecture in across your entire organization immediately. Start small. Start with a single bus per domain. And then find two systems inside your domain that are currently integrated with a point-to-point integration. Move that to events if that's going to be useful for your business requirements. Rinse and repeat. Let's follow that through now. So you've got your order processing domain, you've got your loyalty domain, you've got your fulfillment domain. Each of them have got their own event bus. And that event bus initially is really only going to be used for events inside that domain. And then you look at the applications inside each of these domains. And you're going to start with your order processing service. This is an important one. And you're going to look for services that have a point-to-point integration with each other. You're going to find some applications that are valuable, but aren't your crown jewels. Don't start with your tier 0, fundamentally can't go offline business-critical system, but equally don't start with something that's kind of just an aside system that doesn't really do anything valuable. And finally, find apps that can be changed with reasonably low risk. Don't try and make your 30-year-old COBOL monolith event-driven. Leave that for a later date. And that'll lead you to start with this order processing domain. And you've identified these 3 applications. And you might say, actually, let's focus on the integration between app 1 and app 2 first. So we'll focus on just that one little piece of the system. We'll start publishing events to make that functionality possible. And then we'll rinse and repeat that. And you'll notice that the integration between app 1 and 3 and app 2 and 3 are still synchronous. And then over time, as you evolve this, you slowly move all of your services to be more event-driven. And you'll notice we've still got this big, glaring synchronous line in the middle somewhere. And this is what you can start to challenge as you start to evolve your system. Having these event buses per domain simplifies some of the things around governance, some of the things you'll need to think about. Because you're in complete control over who is able to access your bus, who can access your events. So it simplifies some of the challenges you'll need to get into around that really naughty word, governance. And then as you start to learn the lessons, you learn some of the best practices of building event-driven systems, then you can start to scale that up. Then you can start to think about maturing that across your entire organization. Because now you'll have learned some lessons. Now you've got some best practices in place. And you can start to then set up the routing from these single buses into the centralized event bus. And what you'll notice here is there's still an integration between the loyalty domain and the logistics domain that is synchronous. Because synchronous communication isn't necessarily bad. Remember, like I said, you want to prioritize asynchronous communication where possible, but if you do need some synchronous in some places, then that's OK. When you're taking payments for an order, you probably want to ensure that that payment completes before you do any more. So when you think about this at an enterprise level, as you adopt an enterprise event-driven architecture, there's a few things you're going to want to think about. One of them is governance. You're going to have to think about it at some point. Establish some kind of RFC process, a way to manage the change to the schemas. Think about schema management. Think about how you plan the changes to your schemas. Think about things like idempotency and deduplication. We've not had enough time to talk about idempotency today, but ensure you code for the fact that you might receive the same event multiple times. And finally, use things like the cloud event specification. Use these defined specifications to ensure some consistency across all events in your organization. And finally, remember Postel's law. Be incredibly intentional about what you share publicly, what you share with services outside of your domain, and be defensive, be liberal in what you accept and rely on from others. If you want to dive deeper into the world of event-driven architecture and asynchronous communication, there are some handy QR codes here, some documentation about cloud design patterns, a talk from re:Invent, and of course, Gregor's enterprise integration patterns. I do need to say a really big thank you really quickly. There was supposed to be 2 of us on stage today. The second half of this deck I can take no credit for whatsoever, so thank you, Ben, wherever you are. A massive, massive thank you to all of you, because I know there's other stuff happening out there, so I really, genuinely appreciate you all taking the time to come and listen to me today. If I've got any questions, I'll be hanging around over there somewhere. Thank you all very much for listening.